So we can get started then. Hello, everyone. Welcome to the One World Combinatorics on Words seminar. Our speaker today is Savinien Kreczman from the University of Liège, and he is going to be speaking to us about factor complexity and critical exponent of words in a Thue-Morse family.
Okay, thank you, Nara. Thank you for the introduction and thank you to the organizers for the invitation, and thank you to all for coming. So just before starting, this is, as you can see, joint work with Luka Dvořáková and Edita Plantova. This work was conducted as I was visiting them in Prague last year, and this visit was made possible through funding by a bunch of sponsors. So these sponsors on the Belgian side, just quick question, can you see my mouse cursor as well?
Yes.
Okay, perfect. So these sponsors on the Belgian side and the Czech Technical University on the Czech side. So for today, what I have prepared is a talk about two conjectures on words of a Thue-Morse family. So I will need to introduce these words and these conjectures, and then I would like to explain how we used bispecial factors and the study of bispecial factors in those words to answer the conjectures in question. So the story starts, or at least I want to start the story, with numeration systems. So if you know me, you know that I like numeration systems. And let me start with one that is hopefully known by everyone in this conversation, which is the binary numeration system. So you base it on the sequence of powers of 2, which you can see as a linear recurrent sequence given by the initial condition u0 is equal to 1 and un is equal to un minus 1 plus un minus 1. If you do this, you can express any positive integer as a sum of powers of 2. And if you require that all of these powers of 2 are different, the sum is unique. And so to the number n, you can associate the number of terms in the sum, or rather its parity, and then you get the nth letter of the Thue-Morse word. So that's for the binary numeration system, but you can do something a bit more exotic than that. You can start with the Fibonacci sequence. So to get a good numeration system, you start with the initial conditions 1 and 2, and then un is equal to un minus 1 plus un minus 2. This time, if you want so any number can, of course, be expressed as a sum of Fibonacci numbers, but if you want the sum to be unique, you must require that these Fibonacci numbers are not consecutive. And so once you do that, you can associate with n the number of terms in the sum and its parity, and you get the nth letter of the Fibonacci Thue-Morse word. So here, for instance, I have written the first 17 letters, and every index corresponding to a Fibonacci number is 1 because the sum is just this term. And here the letter 12 is also 1 because it corresponds to the decomposition 8 plus 3 plus 1, which has 3 terms, so 3 is odd, so you put a 1 in this space. You can go even more exotic and use the Narayana numeration system. So this one is based on the recurrence un is un minus 1 plus un minus 3. And once again, you can express any number as a sum of Narayana numbers. And if you want this decomposition to be unique, you must require that all of the numbers involved are not only different, but also non-consecutive. And also, there must be a gap bigger than 1 between two of them. So in a sense, in expansions in this numeration system, any 1 is followed by 2 zeros, whereas in the Fibonacci numeration system, any 1 is followed by 1 0. This time, when you have your unique expansions, with a similar process, you get the Alush-Johnson word named after a 96 article by these two authors. And you have here the first 17 letters again of this word. So now we have 3 named numeration systems and 3 named infinite words that are all obtained using the same process of taking the parity of the number of ones in the expansion in the numeration system. So we can think, well, we did this work for 1, 2, and 3, why not do it for k? And this is exactly what we are going to do. So I will use the recurrence sequence un is equal to un minus 1 plus un minus k, and the initial conditions 1 through k. And then I can build a numeration system where every natural number is expressed as a sum of the un, but there must be a gap of k between two uns that I choose in the expansion. This time the expansion is unique again, and I can build the word xk by taking the parity of the number of ones in this expansion. Okay, so this word is U-automatic. So you know that the Thue-Morse word is two-automatic in the sense that you can feed the binary representation of n to some automaton and get the nth letter of the Thue-Morse word as an output. It's the same for our word xk, except that you need to use the numeration system u rather than the binary numeration system. So you will give the u representation of n to this automaton, at least for k is equal to 4. And this automaton will tell you what the nth letter of the word x4 is. And the way this automaton is constructed is, since you are using the numeration system with parameter k is equal to 4, any letter 1 must be followed by 3 letters 0. So we see indeed that the automaton only accepts words where a 1 is followed by 3 zeros before seeing an additional 1. And then this automaton is simply separated into the northeast side, where you have seen an odd number of ones so far, and the southwest side, where you have seen an even number of ones. And so once you finish reading the word, you know what the parity of the number of ones you just read was. So that's for the U-automaticity, but we have a family of results starting with a result of Chalit and then later developed by Michel Rigaud of Liège, where words that are U-automatic in non-standard numeration systems are morphic, and you can find a morphism based on the automaton in question. And so from this automaton, we can, or I guess for the general version of the automaton with a general k, we can define a morphism and a projection. So the morphism is going to be psi k, and the projection is going to be pi. And then the word xk is obtained as pi of the fixed point of psi k, starting with 0. And this fixed point is going to be uk, and it's going to be quite important in the remainder of the talk. So don't worry, I will recall the shape of the morphism psi k at appropriate times during the talk, so you don't need to memorize this so far, but just note that it is, in a sense, a generalization of the Thue-Morse word, even though the Thue-Morse word is a bit of an edge case in the family, as k is equal to 1. And then you just project according to the decomposition in this automaton. Okay, so that's the word xk, and as an example, here is the word x4, which is going to be a recurrent example in talk, as it's the first generic word, the first non-named word in the family. So you have the word u4, which is the fixed point of psi, starting with 0, and those thicker bars here, they represent the end of a psi n of 0. And then when you project, all the letters 1, 2, 3, and 0 prime go to 1, all the other letters go to 0, and you obtain this word x4. So that's the Thue-Morse family that was mentioned in the title, and now I need to talk about the two conjectures. So the reason that we got interested with my co-authors in this family of words is an article by Jeff Shalit in March 2025 on the archive, where the main focus of the study is the word x3 as well as another projection of the word u3, which is the projection where you delete all the prime, all the apostrophes. And so these words that you obtain from U3 by deleting the apostrophes are linked to another subject that was presented in this seminar on March 11 of 2025 by Pierre Letouze. So this subject is Hofstadter functions. And in the March 25 preprint of Jeff Shalit, there are two conjectures on words of the family XK. And the reason that they stay as conjectures and not as theorems is that the focus of the preprint is to use Walnut to investigate the sequences U3 and X3. And that works very well. But the problem, in a sense, with Walnut is that you need an underlying automaton that is fixed. And all of the sequences XK use different underlying automatons since they are based on different numeration systems. So Walnut can prove properties of XK for any K, but not for every K simultaneously, which is what we will be attempting in this talk. So what are the two conjectures? The first concerns repetitiveness and critical exponent. So to recall, the critical exponent of a word X is the exponent of the longest power, of the highest power of a factor of X. So for instance, in the Thue-Morse word, there are squares which are power 2, but there are no overlaps which are powers bigger than 2. So the critical exponent is just 2. You also have the asymptotic version, where rather than considering any power, you consider powers that occur even for long words. So in this case, you take a limit of the biggest exponent of a power of a long word that occurs as a factor of X. And the conjecture about our family of words is the following, that the sequence XK has a critical exponent K plus 1, which is attained only by these two specific words. And it has a critical, asymptotic, critical exponent equal to 2. And moreover, there is a slightly stronger result, which is that it does not have, in a sense, an overlap of length K. So no factor that is a square and then an extra K letters that match the beginning of the square. So this conjecture generalizes the fact that for the Thue-Morse word, there are no overlaps, which corresponds to the case K is equal to 1 in this statement. Okay, that's one. The other conjecture concerns the factor complexity of the sequence XK, and to be exact, its first difference. So the factor complexity, just to recall, is the number of factors of length n. So it's a function that maps n to the number of factors of length n in X. And then to obtain the first difference, you just take the factor complexity at index n plus 1, and you subtract the factor complexity at index n. And the conjecture is that for xk, the first difference of factor complexity takes only two different values as soon as n is large enough. And those values are 4k minus 2 and 4k. And so these are the two conjectures that we aim to discuss today. And just to cut to the chase, both of these conjectures are true. And now for the remainder of the talk, I want to explain, in a sense, how we managed to prove these two conjectures. So just before we move on to the meatier part of the talk, I want to make a few elementary considerations on the word UK. And so these considerations can be proved by looking at small rosy graphs of UK. The first is, in a sense, the language of UK is symmetric by the operation of adding and removing apostrophe. So if you see the word 3 prime 0 0 prime in the word UK, you will also see the word 3 0 prime 0. So we call the twin of a word the word that is obtained by adding primes to every letter that doesn't have one and removing primes from every letter that has one. So if W is a factor of U, then the twin of W is also a factor of U. That's one. The second thing is that letters occur in UK, in a sense, in a very constrained manner. So if I see a letter J or J prime in this case in UK, it necessarily occurs as a suffix of the word 0 prime, 1 prime, 2 prime, etc. up to J prime. And in a sense, different letters are 0 and 0 prime. You do not have that. Well, I guess you do have that 0 occurs only as the suffix of 0, but that's not very interesting. The interesting thing that you can say is that if a 0 is followed by a 0 prime or by another 0, then it necessarily occurs as a suffix of 0 prime, 1 prime, etc., k minus 1 prime, and 0 here. So if we know a letter, we also know what letters come before in the word U4, in the word U4, I guess, and also UK. Okay. I promised that I would talk about bispecial factors. So just to recall, what is a bispecial factor? It's, in a sense, a factor that you can extend to the left in multiple ways and to the right in multiple ways in your word. So if I have a factor of a word W, I can either extend it in just one way to the left, and then it's not left special. But if I can extend it in multiple ways to the left, it is called left special. And you have right special for the extensions to the right, and bispecial when it is both left special and right special. So in this example here, I have recalled U4 and X4. The word 0 prime, 1 prime, 2 prime is bispecial in U4 because it can be extended to the left by 1 prime and by 3 prime. And it is also right special because it can be extended to the right by 0 prime and 3 prime. So it is bispecial. You will note that when you project from U4 to X4, it doesn't completely preserve bispecial factors. So what we see here is that both left extensions project to the letter 0. And so we do not have any more different left extensions when we have projected down to X4. That's one of the problems that can occur. The other problem is that you can have different words that are projected to the same word down in X4. And so even if those starting words were not bispecial, it's possible that, in a sense, you fuse the two extensions, and now you have multiple extensions to the projection. So that is going to be a problem, but as you will see in the future, we'll manage just fine. We just need to be aware that this can happen. Now, why would we care about bispecial factors? That's the question that I want to answer right now. As we will see, there are strong links between bispecial factors and our two conjectures. So I want to first discuss the factor complexity. There is this, I guess, folklore result that the first difference of factor complexity in a binary sequence and in a recurrent binary sequence, but that is the case of X4 and Xk for any k, the number of less special factors of length n is exactly the first difference of factor complexity at index n. And the reason is simply that if you have W, a factor of length n, that is less special, this means that 0W and 1W are both factors of length n plus 1. And that means that you have one factor of length n that gives you two factors of length n plus 1. So in a sense, this contributes plus 1 to the first difference of factor complexity at index n. So that's for the first part of the proposition. The second part is that any less special factor can be extended to the right in a shortest bispecial factor in a unique way. The idea is just that you extend W to the right as long as that is uniquely possible. And once you reach a point where it's not uniquely possible anymore, this means that it's possible in multiple ways. And so this means that this big factor here has to be bispecial because W was left special, and then you extend to the right in multiple ways. So this links the first difference of factor complexity to the number of left special factors, and then left special factors to bispecial factors. So understanding bispecial factors will help us to understand the factor complexity. As for the conjecture about repetitiveness, the link is provided by this result by Dolce and by my co-authors, which links critical exponent and asymptotic critical exponent to return words to bispecial factors. So just to recall, a return word is a word that goes from the start of an occurrence of W to the start of the next occurrence of W. So if you are familiar with return words, it's reasonable that if a return word to W is short compared to W, then it means that this return word occurs with a high power, because here it's at the start of W, but it's also here at the start of W. But now it means that W starts with RR, so you once again find your R a third time here. And the more short R is compared to W, the more you can repeat this process. So that's reasonable, but the real result of this theorem, in a sense, is that bispecial factors are optimal for this behavior. So if you are looking to get the biggest repetitions, you need only to look at the return words to bispecial factors. So now we have linked our bispecial factors to both of the conjectures. And so what remains to do is to study the bispecial factors, hopefully in XK, but in UK it will already be quite a bit of information. And so what I want to introduce now is a method published by Cloudi in 2012 that allows us to find all of the bispecial factors of UK. So this is a method that applies to circular non-pushy morphic words. So UK is a morphic word, and circular non-pushy, I guess it should say pure morphic words, sorry. And circular non-pushy are just two technical conditions, but those are not too hard to verify. I believe that they are true for any pure morphic word where the morphism is primitive. So this is clearly the case for UK. So we can use this method here, and we will illustrate it with U4. So what is the idea? The idea is to take the morphism, so in our case, Xi4, and turn it into a way to map short bispecial factors to longer bispecial factors. And then the idea is you will start with a small set of short bispecial factors and then apply your mapping to get more and more bispecial factors. And if you do everything right, you will get all of them. And so every bispecial factor will be obtained as an iterated image through this mapping of a small bispecial factor. The idea is that we will consider not bispecial factors, but rather bispecial triplets, which are a bispecial factor and then left and right extensions of this factor. So let's see it in action for Xi4 and U4. So here the word 0, 1 is bispecial in U4. You can see here that it is preceded by 0 and followed by 0 prime. And here I took the liberty to take the twins rather than the word 0, 0, 1 itself, because it only occurs very far in the sequence. But since 2 prime, 0 prime, 1 prime, 2 prime appears in U4, so does 2, 0, 1, 2. And so this 0, 1 here is bispecial. It has the left extensions 0 and 2, and the right extensions 0 prime and 2. And now we apply Xi4 to everything. So 0, 1 is mapped to 0, 1, 2. 2 is mapped 3 here and here. The image of 0 ends with 1, so to the left of this 0, 1, we will have the image of 0, so that ends with 1. So 0, 1, 2 is preceded with 1. And to the right here, the image of 0 prime starts with 0 prime, so we will see 0 prime here. Okay. So that seems to work. Let's do this again. And now we have a problem. We have a problem. Why? Because the images of 3 and of 0 prime both start with 0 prime. So this means that we can no longer conclude that 0, 1, 2, 3 is right special because we only have one extension to the right. Okay, so what can we do? We can try to say, well, this just means, remember, any left special factor is a prefix of a bispecial factor. So we just need to extend to the right and we will see some bispecial thing going on, but further to the right. So we can say, well, let's try to prove that 0, 1, 2, 3, 0 prime is bispecial rather than just 0, 1, 2, 3. So we do this, but we run into another problem. The image of 0 prime is 0 prime 1 prime, which is fine, but the image of 3 is just 0 prime. And so we do not know what goes here to this right extension because we have, in a sense, arrived at the end of the image here. So that's not good, but we have another trick up our sleeve. The idea is if you, rather than consider extension by letters, you consider extensions by longer words, then you will have more length to your image and hopefully everything will work out just fine. So here we say that 0, 1, 2 is extended to the right, not just by 3, but by 3, 0 prime, which we see here. Now, once we apply psi to everything, the image of 3, 0 prime is 0 prime, 0 prime, 1 prime. The image of 0 prime is 0 prime, 1 prime. So we factor out 0 prime and put it in the bispecial factor. And here we have still two different right extensions. And so now we proved that 0, 1, 2, 3, 0 prime is bispecial. And hopefully, if we carefully choose our pairs of left and right extensions, we can do this forever and we will get all of our bispecial factors. And so the notion here that formalizes this carefully select pairs is the notion of Forky sets. So left Forky sets for left extensions, right Forky sets for right extensions. So what is a Forky set, you ask? Well, I'm glad you asked that. I will not be detailing this definition, but I will explain what it means in the next slide. So the idea is a right Forky set, we want it to represent pairs of right extensions of bispecial factors. We want there to be no duplicates, and we want to be able to apply psi to both elements, factor out a common prefix, and then obtain another pair of extensions, so another element of the Forky set, or at least something that's close enough that we can identify it to an element of the Forky set. So that's right Forky sets. We can do the similar thing to the left. And the result of Clauda is that as long as you have these two technical hypotheses of circularity and being non-pushy, these sets will exist. So they may not be unique. There might be different possibilities to choose the Forky set, but at least one exists. Okay. That's nice, but we still need to build it ourselves. So let's build it for U4. Actually, let's discuss the finished project because building it is a bit cumbersome, but the finished project, at least a section of it looks like this. So this is a subset of the Forky set where I have just selected pairs where one of the elements starts with 0. So the reason why I did this will be apparent later. But now I have, well, what do I have? The empty word is a bispecial factor in U4, so I need to be able to see any right extensions of the empty word, and that means I have to see 0 with any letter. So is that the case? Well, I see 0 with 1 here, with 2 here, with 3, and with 0 prime. I do see 0 with 1 prime in these 3 places, and that's all of them because any 1 prime is always followed by a 0 prime, a 2 prime, or a 0 in the word U4. So these 3 together, they make up all of the pairs that start with 0 and 1 prime respectively. And then these three together, they make up all pairs that start with 0 and 2 prime. And the four remaining nodes, they make up all the pairs that start with 0 and 3 prime. So that's the elements of my Forky set. And now what I can do is transform those elements into one another. So let's say I start with a bispecial factor, and then 0 and 1 are my two right extensions. When I apply psi, the image of 0 is 0, 1, the image of 1 is 2, and so these pairs are one word that starts with 0 and one word that starts with 2. So this 0, 1 is going to be transformed into 0, 2. That's the easy case where I do not need to factor out something. What about the case where I do need to factor out something? Well, let me consider 0 and 3 prime 0. When I apply psi, 0 becomes 0, 1, 3 prime 0 becomes 0, 0, 1. I need to factor out this 0, which is what this label 0 here represents. And then I'm left with 1 and 0, 1. So that's a pair that starts with 0 and a pair, of two elements, one that starts with 0, one that starts with 1. So it's identified with this element of the Forky set. So when I see this as my pair of right extensions, I know that at the next step after applying psi, I will have factored out 0 into the bispecial word, and I will be left with this pair of right extensions. So this graph allows me to figure out what happens to my right extensions when I apply my transformation psi. Just the thing that I did not mention is these salmon-colored arrows. So I pictured the subset of the Forky set where one element of the pair starts with 0. But there is also, of course, the twins of all of these, which are pairs where one of the elements starts with 0 prime. And so the salmon color indicates that you need to go to the twin rather than going to this node here. And as I've mentioned, the labels, they represent the word that you will be factoring into the bispecial factor when you cross the arrow. But now we know the behavior of, well, at least this subset of right extensions. And for left extensions, it's actually quite a bit easier, because if you remember the morphism psi, the images of all the different letters end in all different letters. And this means that if you start with different letters, you will never need to factor out the suffix of the images. Whereas since the images of 3 and 0 prime start with 0 prime, we sometimes need to factor out the common prefix. So actually the left part is even simpler than the right part. Okay, and so just to recall, the idea is to start from my bispecial factor, my bispecial triplet with my bispecial factor in the middle, and then a pair of elements in the Forky set and a pair of elements in the left Forky set, and to transform it by applying psi to everyone, factoring out the longest common prefix of psi of SR and psi of TR, factoring out the longest common suffix here, and I obtain my new bispecial factor. And then the rest of the images can be identified to another element of the Forky set. And now I have obtained a new bispecial triplet, and I can apply psi again, and so on and so forth. Okay, so the idea is, if I choose my initial factors in my initial triplets well, I will obtain all my bispecial factors by iterating this process. Now, what does it mean to choose my initial bispecial triplets well? Well, again, Claudia gives us the answer, and it goes through the notion of synchronizing points. So what is a synchronizing point? It is a factor where you know that you are at the end of an image, or the start of an image, I guess, when you substitute your morphism. So perhaps it's easier to explain on the example of the Thue-Morse word. if you see 0, 0 in the Thue-Morse word, you know that this left 0 is the right of an image of a letter, and this left 0 marks the start of an image of another letter. So that is a synchronizing point. On the other hand, if you see 0, 1, you do not know if this is an entire image or if this 0 is the end of an image and then this 1 is the start of a new image. So that's not a start, not a synchronizing point. So why do synchronizing points help us? Well, the reason is that if you choose all the bispecial factors that have no synchronizing points as your initial bispecial factors of your initial bispecial triplets, then you will indeed obtain all of the bispecial factors as images of those ones. So our well-chosen initial set is the set of bispecial factors that have no synchronizing point. In our case, what does that look like? Well, in U4 and more generally in UK, there is a synchronizing point to the left of every letter except the 1 and 1 prime, and there is a synchronizing point to the right of every letter except 0 and 0 prime. And since every letter has a synchronizing point next to it, this means that the only initial bispecial triplets are the one where the word in the center is the empty word, which will be very helpful for us. And the reason that I only mention this subset of the Forky set is precisely this. When you apply your transformation to a bispecial triplet that has the empty word at the center, if you do not add to the center by factoring out a common prefix or a common suffix, you stay with the empty word in the center, of course. And since we are interested in generating all bispecial factors, so all non-empty bispecial factors, we can just consider starting points where we will add something to the center. So we only need to look at starting points that are the origin of an arrow that has a label, because these are the arrows where you stop having the empty word at the center and you start having a non-empty word when you apply the transformation. And actually, if you look at the Forky set, the other elements that start with something other than 0 or 0 prime are only the origin of arrows that have no label. So when you stay in that part of the Forky set, you stay with the empty word at the center. So really the only interesting bits are the ones that occur here. So we have 4 arrows that have a label, and these correspond to 4 different starting points that are interesting. And so all of the bispecial factors of UK are obtained by iterating my transformation psi on one of these 4 starting points. Or their twins, but the twins are always implicitly present. So just a quick note, the fact that we have 4 starting points here is not linked to the fact that we have chosen U4 as our example. If you choose UK rather than U4, the impact on the Forky set is that those horizontal parts get stretched. You put more nodes in each of the 4 horizontal lines, but you keep the structure with 4 horizontal lines, and the 4 starting points are at the start of those lines. So even if you choose UK rather than U4, you only have 4 starting points. This is nice because it means that we can finally know every bispecial factor in U4 or in UK if you want. We just need to choose one of the 4 starting points, apply the transformation psi, and see what happens. And not only will we know all of the bispecial factors, we will also know their possible left and right extensions, because we maintain bispecial triplets rather than just bispecial factors. We know what will be here to the right and here to the left, and so we know what the extensions will look like. So just as an example, for T1, these are the first few elements that you obtain by iterating Xi4. And so you can see that once you reach this point, you will not be doing anything weird with the center, because on 0 prime 0, there is a self loop that has no label. So starting from this point, there will not be a factoring of a left common prefix, and there will not be a factor of a common suffix here. So starting from this point, you just apply Xi to the center to obtain all of your bispecial factors. And so here, what we obtain is that every Xi4 to the power n of 0 is bispecial in U4. Furthermore, we know that the left extensions can be any letter because we had the choice of letter here with the asterisk. So we did this for the starting point T1, but we can do this for the other starting points. And we get this proposition that characterizes the bispecial factors of UK. So those bispecial factors are the images of 0 by any power of Xi k, and this special guy here, which is Xi k to the power n plus 2k minus 1 of 0, then Xi k to the power n of 0. And also their twins, as usual. Furthermore, we are also, if you remember, interested in left extensions. And so the left extension of these can be anything, but the left extensions of the special factors here, we only have two choices that depend on n. And so here are the first few values of n and the corresponding left extensions, again, in the case where k is equal to 4. Okay. So we are nearing the end of this detour to true Claudas method, and we will be shortly moving back to our two original conjectures. But just one last note on UK. Since we know the bispecial factors, we can study their return words, and using the result of Dolce, Dvořáková, and Palantova, we know now that the word UK is going to be overlap-free. It's going to have squares, but no higher powers. Okay. That's the second section of the talk done, and now I will be moving to the third section where I actually prove the conjectures. Okay, so what did we have as conjectures? The first conjecture was about factor complexity, and we said the first difference of factor complexity is the number of left special factors of length n in xk. So I'm now interested in the left special factors of xk. And I know that these are the prefixes of bispecial factors of xk. But as I've mentioned earlier, bispecial factors of UK and xk might not correspond one-to-one, because I could be merging two different left extensions into the same when I project, and so I lose the fact that it's a bispecial factor. And I could also be merging two different factors and combining their left and right extension and gain a bispecial factor out of nothing. So I have two lemmas that allow me to deal with these two problems. The first lemma basically says that if you have two words that project to the same thing but disagree on every letter, then those words are short. And furthermore, their images, once you project them, are very constrained. So there are powers of 0 or of 1. The second, so that's for projecting different words onto the same, and it becomes bispecial. And the second lemma is about the projections. So you do not want the projections of two different right extensions to match too closely. And thankfully, this lemma tells us that if you have a bispecial factor, the right extensions will quickly differ even when you project them. And quickly means you can have at most two letters of equal projections, and then you have different projections. And furthermore, if the bispecial factor is long enough, this corresponds to the third case, and then the right extensions immediately differ even when you project them. So that is for the other problem that we could have. And now, using these two lemmas, we prove a third lemma that matches makes a link between the left special factors of xk and the left special factors of uk. So this lemma tells you that any left special factor of xk is a left special factor of uk projected, and then you add some small power of 0 or 1 just before. So how does this lemma work? Well, you consider w a left special factor of xk. It must be extended to the left by 0 and by 1, and so 0w and 1w have pre-images, and this gives you two pre-images of w, which are u and v. So u and v both project to w, but I will now take this Solomon block here, which corresponds to the leftmost and maximal block where u and v are actually equal, rather than just projecting to the same board. So here, these two blocks are one and the same. Now to the left, this means that these two blocks differ on every letter, since I have chosen the Solomon block leftmost and maximal. These two differ on every letters, and this means that lemma 1 can be used on them, and so this block is short. To the right, if these two exist at all, it means that the Solomon word here is bispecial, since it can be extended in two ways, to the left in u and v, and it can be extended to the right in two different ways in u and v. And now we can use this lemma 2 here on the projections of right extensions of bispecial factors, since these two words are right extensions of a bispecial factor in Solomon here, and these two words project to the same thing. So the lemma tells us that the rightmost block has to be short. And furthermore, if the rightmost block exists at all, the Solomon block also has to be short. So once you consider bispecial factors that are long enough, you cannot make it out of three short blocks, and so this means that the rightmost block cannot exist. So what you actually have is this Solomon block extends all the way to the right, and it corresponds to f. It projects to the suffix of w, and then the two parts here, since we have applied lemma 1, we know that their projection is a power of 0 or a power of 1. And so this lemma is proven at last. But now I know the left special factors of xk. I know that they are a projection of a left special factor of uk, and then some small power here. But I know, in turn, that the left special factors of uk are prefixes of bispecial factors, and I know the bispecial factors of uk. It's either this one or the other one here. And so starting with the image of the psi n of 0, it can be extended to the left by any letter. And so when I do my computation and consider further extensions to the left and see what it means for the projections when I precede it by some power of 0 or by some power of 1, I will see that 0 to the L pi of f and 1 to the L pi of f are always left special as long as L is in this range, left special in xk. So that gives me 2k minus 1 left special factors. And when I consider the twin of f in addition, I obtain a total of 4k minus 2 left special factors. For the other case, this special factor here has two left extensions, which will correspond to one left special factor in xk. And when I consider the twin as well, that gives me an extra two left special factors. And if I take a look at the length of all of those left special factors, I will arrive at the first conjecture, which was that the first difference of factor complexity of xk is either 4k minus 2 or 4k. So that is proved. The other conjecture was about the repetitiveness of the word xk, and in particular, the fact that it does not have an overlap of length k, so a word of length 2n plus k and period n. So the way I prove this is I proceed by contradiction, assume that such an overlap exists, and take its pre-image. So U is now the pre-image of an overlap, which means that the blue arcs here going from 0 to n plus k and from n to 2n plus k project to the same word. And once again, I consider block where not only do they project to the same word, but they are actually equal. And again, I take these blocks leftmost and maximum. So here the block from I to j and the block from n plus I to n plus j are actually equal rather than just projecting to the same word. But now to the left, I can apply lemma 1 on words that disagree on every letter. To the right, I can apply lemma 2 on right extensions of bispecial factors. And in the center, well, since I know that UK has no overlap, I know that these Solomon blocks cannot overlap. And so I have three conditions on the middle, the left, and the right. And actually, these three conditions turn into very strong conditions for I and J, and sufficiently strong, it turns out, to be able to rule out all the remaining cases by hand. And so once I do that, I have proved that no overlap of length k exists in xk. So that's the first part of the conjecture. The fact that it has asymptotic critical exponent equal to 2 immediately follows. And the fact that it has critical exponent less than k plus 1 or equal to k plus 1 follows from taking n is equal to 1 here. And since 0 to the k plus 1 and 1 to the k plus 1 are factors of xk, the critical exponent must be equal exactly to k plus 1, which proves the second of the two conjectures. So that is the end of the path that I wanted to walk. So just to summarize, we have not developed but used the method of Clauda to identify not only bispecial factors, but also their left and right extensions. And in our case, it worked really well because the fact there were lots of synchronization points in our morphism. So there were not a lot of starting points for our transformation side. Even then, we still had to do a little bit of technicalities at the end, but we managed, and we managed to prove the two conjectures that I stated at the beginning. So that's all that I have for you today, and I thank you for your attention.
Great, thank you very much, Savinien. Does anyone have any questions? Hajime.
So thank you for nice talk. And may I see page 28?
28, this is the one.
Yes. I'm sorry if you explained this, but is it possible to characterize n such that the difference is 4K?
That's a good question. I guess we have information on this. So we have not done it, but you know that the difference is 4K when you get these extra two bispecial factors, left special factors coming from this. So basically, it's going to be more or less between the length of psi k to the power n plus 2k minus 1 of 0 and the length of the complete word. It's not exactly that, because you also have the prefix that messes up things by a little bit. But yeah, up to k, it's going to be words that are in between this one and the big one.
Thank you.
Jeff, did you have a question?
I didn't have a question, but I just wanted to say thank you so much for thinking about my two conjectures and especially for proving them.
Well, you must also thank Edita and Luca then, because they are the one with the initial ID.
Of course.
Thank you.
We can hear your thanks, and we are pleased.
Savinien, can you remind me again, what was kind of the original motivation for studying UK and XK? I guess maybe by Jeff, or was it Jean-Paul?
So, well, it's in a sense a natural extension of the Thue-Morse word. It's linked to some easy numeration systems in a way, and there is also the link to Hofstadter functions. So Hofstadter functions are a family of functions that are defined using recursive definitions. And basically, you have one function for each of the numeration systems. And it's linked to the word where rather than using this projection, you project by removing the primes.
Okay.
I do not recall the exact nature of the link, but it should be findable, for instance, in this presentation.
Okay, great. Thanks. Does anyone else have a question? All right. If not, thanks again, Savinien.